In this lesson, we're going to build on what we know about acids and bases and actually talk about the reactions that can occur. To start this off, let's introduce this idea called conjugate acids and conjugate bases. So how this works, first of all, the word conjugate you may be familiar with already. You probably heard about it when you talk about changing verb endings in different languages to make them match, and same thing with adjectives and such. So conjugate is sort of like that same idea. You have to change something and sort of find that there's like a counterpart. When it comes to conjugate acids and bases, the start to this is basically looking at the Bronsted-Lowry theory. Remember, the Bronsted-Lowry theory refers to there being an exchange of H+, right? So one substance will give up an H+, the other substance will accept the H+. That's the Bronsted-Lowry theory. And so what's key here is keeping track of the H. Where does the H go? Where does it end up? And that's where this whole point gets us, and that's exactly what's going to help us be successful with these discussions. First of all, conjugate acid, right? So the conjugate acid, let's back up for a second, actually. So if you talk about protons, right, trying to give up substance, the acid, the Bronsted-Lowry acid, right, that's something where the H plus is donated, right? We're giving it. We're giving to something else. But the Bronsted-Lowry base, right, that's going to be where the H plus is accepted. Okay, so remember there's going to be H plus given off, H plus accepted. And so you actually form some new terminology. The conjugate acid, right? This is the substance that is formed when a base accepts the proton. So this H that is given off, something else is going to take it. The thing that took it, right, becomes something new. And we designate that as the conjugate acid. The conjugate base, then, on the other hand, the conjugate base, this is a substance that remains, that's left over after the acid has donated a proton. So if you notice, it's kind of a bit of a contrast. Sounds like a contradiction, I suppose. The conjugate acid, right, that's related to what happens when a base does something. The conjugate base is something that happens when the acid does something. So they're kind of like a counterpart, right? Let's put this into action here on this bottom equation here. So it's probably a little bit messy first. Let's go and see what's going on. All right, we have HF, hydrofluoric acid. You got water. It's in equilibrium with H3O+, hydronium, and F-. All right, so the key here, again, we're just looking at this as a Bronsted-Lowry combination of Bronsted-Lowry acid, Bronsted-Lowry base. So we're looking at H+ transfer. Okay, so looking at my reactants and looking at my products. What seemed to have happened? Well, H, right, looks like H came from the HF and was thrown onto the H2O. To make H3O+, right? And then the F- is left over after the H is donated. So how then can I do this? If I'm going to look at this and identify everything as an acid or a base, I'm going to start off by saying that this is my acid, right? Remember, that's the substance that gives up the H+. This is now my base, because that's the substance that accepts the proton, the H+. So the language here, it says the conjugate acid is a substance that's formed, that's created, that's made when a base accepts the proton. Remember, this is my base. It accepted protons, so what is the resulting substance is H3O+. So this becomes my conjugate acid. I'm just going to be lazy and just do Ca, saying it's the conjugate acid. So that's going to be related to the base accepting a proton. My base is the water, accepts an H, becomes H3O+. What about F-? Well, F-, that is the substance that remains when an acid, HF, donates the proton. So the HF gives up the H. What's left over is the F-. This becomes my conjugate base. Okay? So these are like the counterparts, right? These two things right here are effectively counterparts to each other. The acid becomes the conjugate base. The base becomes the conjugate acid. Now, what exactly is going on here? Remember, this is supposed to happen as a sort of a back and forth. How do you know this is kind of happening back and forth in both directions, going both towards the left, excuse me. You're both going towards the left and towards the right. Well, remember, this is also an equilibrium. This equilibrium arrow means that they're going back and forth. And so this reaction, we always generally tend to go from left to right, but because this one can't actually go backwards from right to left, that means something also has to change. It's still going to act like a Bronsted-Lowry acid and base. And so this conjugate acid, well, what do you know about the behavior of acids? Acids give up electrons, right? They give up protons. And so if they give up a proton, give up an H+, it's going to go from this guy to this one to then reform the original HF and the H2O. So this is acting as an acid. This is acting as a base if the reaction were to go backwards that way. So technically it acts as an acid, it technically acts as a base because this is giving up the H, this is accepting the H to reform these original reactants. So acid base on the left side, this is our original substance. Conjugate acid, conjugate base, these are the resulting substances as these two do their thing. So here's some other examples. I've given you 3 reactions. You're being asked to identify the acids, you're asked to identify the base, and then asked to identify the conjugate acid and the conjugate base in the following ones. I'll go and start you off on the first one. All right, so this one right here, you have HNO3, you have H2O. HNO3, this substance looks like it's giving up the H, right, because it results in NO3 over here. And the H2O then accepts that H, right, that very same H that came from here. That means this is going to be the resulting hydronium ion. So this is my acid. This is my base. This then is my conjugate acid because it accepted the H plus, right, to become this. And this becomes my conjugate base. Go and try this out for the next ones, right? Seeing where you can identify, track the pattern of the H, see where it goes, see where it ends up, and so on and so forth to make those decisions. All right. We're also going to briefly talk about strong acids and strong bases. So you should probably recognize these are basically the lists of acids and bases that are around. And strong acids are ones that completely dissociate. Anything else is considered weak, so make sure you review this. You're also going to have the list of strong bases. These are substances that we don't really talk about much, but if you notice, all of these bases here are OHs, right? They all end in hydroxide. They all end in hydroxide here. And these are our strong bases, so that means any other base that's around, right? If you look at the behavior of the compounds, any other bases that are around, those will be weak bases because, even though they might accept an H+, they might not have hydroxide. But these, again, are definitely the strong bases. Any other base that we talk about are going to be considered weak bases. Finally, we're going to have a neutralization reaction. These are probably something you are somewhat vaguely familiar with already. A neutralization reaction is one that occurs between an acid and a base. Right? So the acid and the base, they neutralize each other, almost as if they're both kind of like active and they have this way of canceling each other out. This most frequently occurs between in aqueous solutions. Right? So aqueous solutions of an acid, aqueous solution of a base, the two together, they're going to have a neutralization occur. Generally speaking, there's going to be 2 products as well. You have always liquid water and you always have a salt. Now, this word salt we've talked about before. The word salt, a lot of times we just think of sodium chloride, right, NaCl. But this context, really, the salt is just the resulting ionic compound. Right? And we're just going to generically call it a salt. So anything that results in an ionic compound of some kind, that resulting ionic compound is just called a salt. For example, sodium hydroxide hydrochloric acid. Right? So HCl, NaOH, both of these are aqueous, right? They're both in watery environments. These two react together. It's an acid and it's a base, and therefore it's going to make a water product and a salt. Now, coincidentally, this is literally NaCl, like sodium chloride, but it's not always going to be that. Now, how exactly does this work? Remember that you have acid-base reactions. There's something giving up H's, something taking away H's, absorbing the H. And if you follow the pattern here, what does it kind of look like? Well, remember, this is HCl, right? This is aqueous, and that means as an acid, it's going to separate into some ions. And as we just said, the NaOH on the previous slide there, NaOH is also a strong base, so that's going to also separate into its component ions. If you notice underneath it, you actually have these 2 guys right here written just to basically represent that idea that they're separating to ions. And these, again, are just all floating around, these 4 different ions. The H+, the Cl- are all floating around, right? The H3O+, the Cl-, those are all floating around. Na plus and OH minus, those 2 are floating around independently, right, because they are strong electrolytes and they completely separate. And so eventually they kind of bump into each other, right? They eventually will try to react. And some of them are successful, some of them aren't so much. But this one right here, H2O, right, what seems to be combining is the H plus from that guy, the OH minus from that guy, together to make H2O. And then, on the other hand, you have Cl minus floating around and Na plus floating around to make the NaCl, to make the salt. So you have water and salt produced from this reaction. I don't know if you kind of remember this, but this is vaguely reminiscent of double replacement reactions, right? Because you have 2 basically ionic substances that are going to swap ions. And this is, again, kind of like that. HCl is not an ionic compound, but it does separate into ions, so it effectively works the same way. So this is basically a neutralization reaction. As always, right, you should be mindful of how you write these out. So make sure that you're forming H2O liquid, right? That's a liquid substance that's generated. NaCl is actually going to be aqueous. That's actually dissolved in water still, right? It's not going to make liquid sodium chloride. You don't see all of a sudden an ionic compound that's a liquid layer somewhere in there. It's dissolved. And that basically takes care of it. So that's your neutralization reaction. And that's going to have acids, bases that react with each other. To wrap this one up, we're going to go ahead and take a look at sort of what happens on the particle scale. So you'll have to do a little squinting here, but I think you'll be able to see it. This effectively represents what we've been talking about. So you have the H3O and Cl minus. Where does that come from? That comes from the HCl that's separated, right? These two separated, they're different ions. Well, probably should draw it upwards to reflect that. Cl minus goes there. H corresponds to the hydronium ion that forms. On the right side, you have Na plus and OH minus. Again, that comes from, I'm going to squeeze that in here, NaOH, right? The Na plus corresponds to that. The OH minus corresponds to that. And then you have NaCl, right? That's going to be from the sodium chloride that was produced, and then water, right? Good old water here. What you notice then is that this diagram right here on the bottom, these particles are basically representing what happens. So this effectively is where I'm going to kind of draw a little separation point. So this is kind of what they're showing here, is that this container over here has some volume of water, this one has some volume of water, and each of these has some stuff dissolved in it, right? So these are your hydronium ions, these are basically your H pluses floating in here, right? And then you have your, let's see, Cl minuses, chloride ions showing up right here, right? So this corresponds to that. Let me do this instead. Chloride ions, hydronium ions, that corresponds to each of these. And that corresponds to each of these there. And then over here in the blue, you have the sodium ion that corresponds to that, right? And then you have the hydroxide that corresponds to this. I don't know if you can really see that. It's a red and a blue atom to represent the hydroxide. And they're all separated. They're all strong acids, strong bases. So each of these circles represents the fact they're completely separated. And finally, you mix them together, you end up getting a new solution that the NaCl has, right? So what happens here is that the Na is still floating around as independent sodium ions. Cl is floating around as independent net ions. But then what else you have is a bunch of water, right? Nothing else. You don't have any other ions. You just have Na and Cl ions floating around. So Na technically, I guess, applies to that. Cl applies to that. Either way, right, so in this diagram, it looks like, or in this picture, it doesn't look like much has changed. Still clear solutions. That's expected. But basically what is in here now is just a bunch of salt water, right? Just a bunch of dissolved salt in some water. And if you were to evaporate the water away, you would just generate that. All right. Finally here, we have some practice. Let's go and see how this works out. The first two, again, you are given the formulas and such. The last two, you're going to have to translate them yourselves. So you might want to review how to do some acid-base nomenclature. But effectively, HClO4, right, that's going to be your first one. NaOH is going to be your second one. And we know that these are going to be in acid-base reactions because this is an acid, and that's a base. So it's going to be an acid-base neutralization. So what we're going to do here is generate the two products we're always going to have. You're always going to have water. You're always going to have a salt. So let's go and write those out. Water will always be produced, right? It's going to be a liquid. Now, again, what did it take to make that water? It took the OH from here. It took the H from here. So that's going to be the water part. Whatever's left over is going to be your salt. Remember, ionic compounds, they always have the positive ion written first, the negative ion written second. So you'd always make sure you write the Na, which is positive, first. ClO4, which is perchlorate, that's a negative. That's written second. HClO4. And this is going to be a positive one. This is a negative one. So you only need one of each to write a legitimate compound as your salt. And then finally, to wrap it up, you do know that this is dissolved in water, so it's aqueous. So a couple things here. Remember, always write legitimate compounds, right? H2O is a legitimate compound. NaClO4, that's the legitimate compound, right? With the positive one, negative one. And then you start balancing and adding the states of matter. So we're good there. What about the second one here? Let's go and take a look. Well, we have HBr. H is an acid. It starts with an H anyway. We know this is hydrobromic acid. This is barium hydroxide, right? That's going to be a base. So these two are going to undergo an acid-base neutralization. Acid and a base. What are two products? It's always going to be water, H2O, liquid, right? And our other salt. All right, let's figure this out. So we know we have OH here. We know we have H here. Those two are going to combine to make water. All right, that part's taken care of. By the way, some of you are wondering, wait, I thought we had two here. Where did they go? They just disappeared. Remember, these are all separated ions, right? This is actually going to be some combination of barium 2+ ions and a bunch of OH- ions floating around, right? They're basically separated at this point. It didn't look like that on paper, but you have to think that. And so the fact that there's two here, that doesn't play a role yet, right? That's going to be something we discuss later on when we balance. But of course, write legitimate compounds. You can possibly write anything else other than H2O for water. What's left? Barium ion, bromide ion, right? So you're going to have barium, that's your 2+ ion, that's positive, it's going to be listed first. Bromide listed second, Br with a -1, you have double of those. And of course, that's going to be an ionic compound that's dissolved. All right, so the very last thing we have to do is do some balancing, and to do so we add some coefficients. We're probably going to have to do a little bit of this and a little bit of that. And there you go, that's done. So as always, right, write legitimate compounds for your neutralization reactions after identifying what your acid, identifying what your base is, and then fill in the rest. All right, try out number 3 and 4, and that'll do it.